Good evening, everybody, and welcome to the 60-something in the series of Great Minds, Great Lives, Fireside Talks. And tonight we have an extraordinary privilege and pleasure of listening to Dr. Robin Catchpole of Cambridge University, formerly senior astronomer at the Royal Observatory in Greenwich, a very, very distinguished scientist and astronomer, and a wonderful purveyor of the mystery and the wonder and the magic and the science of space. Now, Robin was telling me just a moment ago that I asked him who his favourite star was. I asked the same question to David Thompson, the great writer about film, who was on 2 or 3 nights ago. Got a different answer from David Thompson. And if we're very lucky, we might hear from Robin what his favourite star is, because he does have one. And if, like me, you imagine that astronomers always walk around with a slight crick on their necks because they're so used to walking around looking upwards, I can tell you that Robin, as you're just about to see, is entirely normal looking and just a wonderful, wonderful communicator. Thank you very, very much, Robin, for joining this University of Buckingham Fireside Talk tonight. So Robin is going to talk for some 45 minutes. Do have questions ready, please, on anything that you've always wanted to know about the universe, but never dared ask until now. This is your moment. And Robin, this is your moment now. Over to you.
Thank you. Thank you, Sir Anthony. I will start now then. So I'm going to tell a story. And like all good stories, we should start at the beginning. So I want to take you back 14,000 million years to a time when the universe was a few seconds old, almost to the very beginning. Although cosmologists will tell you the really interesting stuff had happened by the time the universe was a millionth of a second old. Now, what we see in this graph, we see time along the bottom here and declining temperature up the side here. You'll see it's not a linear, it's not even logarithmic. It comes in sort of important intervals, if you like. The universe, when it was about 3 seconds old, was at a temperature of 10,000 million degrees or so. And it was a seething mass of protons, neutrons, electrons, and photons, as well as the mysterious dark matter. For the next few minutes, until the temperature drops to a mere 1,000 million degrees, conditions are like those inside a star, and hydrogen is being converted into helium and a little bit of lithium. After 3 minutes, the temperature has dropped and the fusion reactions cease, and we end up with a mix of 75% hydrogen and 25% helium by mass. For the next 300,000 years, the universe continues to cool and expand. And if we could be there, we'd find ourselves inside a very hot, luminous fog. We wouldn't be able to see very far at all. But after 300,000 years, the temperature has dropped to about 3,000 degrees. And at that temperature, the electrons combine with the hydrogen and helium nuclei, and the fog clears. And for the first time, the universe becomes transparent, allowing photons to travel in straight lines. Since then, the universe has expanded about 1,000 times in size, stretching the wavelength of these redshifted photons, which we see today as the microwave background. But before I show you the microwave background, I just want to remind you that we can show the entire night sky on a flat map in the same way that we can show the entire sphere of the Earth. And this is a projection that distorts the shape of continents, but keeps their areas the same. So the light of the microwave background is highly uniform all over the sky and has a temperature of about 2.7 degrees above absolute zero. But to see any interesting detail, we must increase the contrast by a factor of 100,000. And now we can see tiny fluctuations encoded in these colors, red to blue, of temperature and density. And if you look carefully, you can see there's a dominant mottling texture that has a scale of about 1 degree. And these very tiny fluctuations of density are the source of all stars and all structures that exist in the universe today. And in fact, they owe their origin to quantum fluctuations in space-time in the first few minutes of the Big Bang, few moments, not minutes, moments of the Big Bang, 10 to the minus 36 seconds or so. Now, the universe continues to cool and expand, and we now enter what astronomers call the Dark Ages. Because if, once again, we could transport ourselves back to that time and looked around, the universe would have gone completely black. All the photons, they're all still there, but their wavelengths have been stretched into the infrared, so we can't see them with our eyes. But gravity, the weakest of all the forces that nevertheless controls the evolution of our universe, is drawing matter together into inside those tiny density fluctuations and increasing the amplitude of them. And these mass concentrations get greater and greater. They fragment, increase in density. The increasing force of gravity as a result of the mass getting together then rapidly collapses them, raising their internal temperatures and pressures until nuclear fusion reactions burst into life, halting the collapse, and the very first stars are born. This is when the universe is, we think, about 600 million years old. We've not yet been able to look far back in time and space to actually see these stars, so this is an artist's impression. And these stars are very different from all subsequent stars, as they're made of pure hydrogen and helium. This allows them to grow perhaps 1,000 times the mass of the sun. Today's stars can only be about 100 times the mass of the sun. They will, as a result, have very short lives, maybe 100,000 years or less, before exploding as supernovae and adding heavy elements to the gas clouds and leaving behind black holes. And it's possible that these black holes may be the seeds of the supermassive black holes that are found in the center of all galaxies today. From that moment onwards, from the birth of the first stars up to the present day, 14,000 million years later, the birth and death of stars carries on in very much the same way as it does till the present day. And it's important we should have a quick look at that. And within galaxies, stars are born from clouds of mainly hydrogen and helium, of course. They shine until their nuclear fuel is exhausted and die, and in the process add their own contributions of elements to the interstellar clouds, which will give rise to a new generation of stars. These nuclear fusion reactions build hydrogen and helium up the periodic table. Low-mass stars like the Sun live for maybe 11,000 million years before becoming red giants and then planetary nebulae and white dwarfs, while high-mass stars evolve much faster and after a few million years end their lives in giant supernova explosions, and both steadily increase the proportion of elements beyond helium in the periodic table, steadily increase those proportions in the interstellar gas, out of which subsequent generations of stars are born. And so now we come essentially to the start of our solar system, and the slice of rock you can see between my fingers is the precious product of stars that lived and died in the first 2/3 of the life of the universe. And so this object was created about 4,500 million years ago, at the time of the birth of the sun and the planets, and it's formed out of material left in the disk around the around our newborn sun. There's one in Orion, a disk around a star that is being born. As a result, this rock is older than any rock on Earth. It was never incorporated in a planet or an asteroid, and in fact fell to Earth as a meteorite in 1969. Apart from the gases, it contains all the elements in the periodic table. And in fact, it is the sine qua non, the origin of everything on Earth, all life, all the trees, all the rocks, and of course, even ourselves. So how do we know these things? Well, by using the laws of physics to interpret the message that light brings us from stars and galaxies across the universe. And what I've done here is put a diffraction grating in front of my camera so that I can read the message from the streetlights. There's a row of streetlights over on the right here. The grating breaks the light up into its component colors, and we see here a pattern of bright emission lines that are in fact the unique signature of the element mercury. And if I was to measure their relative brightnesses of the different emission lines, I could work out the temperature and pressure of the mercury vapor inside the streetlights. And if I measured their wavelengths very, very carefully, I could measure the Doppler shift, and I could find whether or not I was falling off my balcony when I took the photograph. Now, the other great valuable property of light is that it travels at a finite speed. In 1 second, light can travel 7.5 times around the world. So if you take a tennis ball and wind a piece of string around it 7.5 times, then unwind the string and hold it out between open arms, as you can see in the picture, on the scale where the tennis ball is a model of the Earth, the string represents the distance that light travels in 1 second. So if you like, it's a distance of 1 light second. And to give you a sense of scale, on the scale of this model, well, the moon is about 1.2 light seconds away from the Earth. So it's a very nice demonstration because you can see it's something you can hold out in your opened arms. So a light year, which is the unit that we're going to use for distance in this talk, is merely the distance that light travels in one year. It travels 300,000 kilometers in a second. So you just have to multiply that distance by the number of seconds in a year. So the finite speed of light gives astronomers a unique advantage over every other science, as it allows us to look back in time as we look deep in space. And the deeper we look in space, the younger we see the universe. So we can't look back in time where we are, we can only look back in time and more distant places. But so, in other words, when you look up at the universe, you're not seeing it all the way it is now. In principle, you're seeing the whole history of the universe, with the older bits ever further away. And we can make a timeline representing all the time in the universe and mark on it events. There we are. Here's today, you see, the future up there, the present back here. And we can mark events like the birth of the sun and the birth of the Earth and the multi-celled organisms appearing also there. And we can mark other things that we're going to observe, like the microwave background. And here we've got the Big Bang. And so the stars that actually we see in the sky, and even the nearest galaxies, are less than the thickness of this arrow away from the present moment. And it's only really in the last 30 years or so, since the advent of the Hubble Space Telescope, that we've been able to look deep and back in time a significant distance to see the universe when it was very different from the way it is today. If we want to put ourselves on that diagram, we have to take the last 100 million years, which is just there, expanded, and then take the last 7 million years, which is about the time when we and chimpanzees had a common ancestor. And of course, we've both been evolving since then, and modern humans appeared maybe 300,000 years or so ago. So let us now start our exploration of the universe using the speed of light as our yardstick. And here is the sun. It's 498 light seconds, or about 8.3 minutes from the Earth. And if we proceed outwards, here we've got a portrait of the whole solar system taken by the Voyager spacecraft back in 1990. And there's the sun, and in fact, Mercury, Venus, Earth, Mars, and Jupiter are lost in the glare of the sun, and we see Saturn, Uranus, and Neptune. And Neptune
Robin,
Robin, yes?
Can we just go back one slide, because there was something intriguing there about the bird.
Oh, yes. Well, this was just a sort of symbol of the bird represents our Earth, if you like, and then you've got Venus in transit across the sun on this particular occasion. So it kind of links us, us as the observer to the sun 8.3 light minutes away. So it was just a fortuitous image that happened to have a bird in it, and I rather like that. Okay, I will go back to our view of the solar system. And Neptune is the most distant planet, there it is, and it is 4 light hours from the sun. So we've gone from 8 minutes or so from here to there to 4 light hours, 4 hours to that position there. But now we must travel 4.4 light years to get to the nearest star. And this star is called Proxima, or Alpha Centauri. It's actually Alpha Centauri. Proxima is a very, very faint star, slightly closer, and it is the nearest bright star to us. It's a star, in fact, very like the sun. So if you went over to that star and looked back at the Earth would appear about as bright as that. And you will notice the other pointer, this is only visible in the southern hemisphere, is more than 100 times further away, and so that's 100 squared, so 10,000 times. It's actually 7,000 times brighter intrinsically, so that it appears the same brightness on the sky. As the sky gets darker, we can look deeper into space and see the Milky Way. We won't see it quite as bright as this, but many of the stars that we see in the night sky are typically between, well, some of them are as close as 10 light years, but many of them are hundreds to thousands of light years away. And the two blobs, this is again the southern hemisphere, are the large and small Magellanic Clouds, and they are actually satellite galaxies of our galaxy, and they're about 160,000 light years away. So they're much further away than most of our galaxy. So this image again shows the entire night sky, and with the Milky Way along the middle of it. And it's not actually a picture in the conventional sense. It is actually a plot, though they're not all plotted here, of the 1,000 million stars that are currently being observed by the Gaia satellite. That's about 1% of all the stars in the galaxy. And so it's just a plot of stars. And we don't have time to talk about the Gaia satellite, but it is revealing an enormous amount about the structure of our galaxy. And notice these patches of cloud. Actually, they're just the absence of stars in this particular diagram, but they show these patches of relatively nearby clouds in our own spiral arm that are obscuring our view of the central regions of the Milky Way. There are the Magellanic Clouds down there. But if we use an infrared telescope, we can penetrate the dust and gas to clearly reveal the central bulge of our galaxy and the fact that there is a disk. So the relatively nearby stars appear all around us, all over the sky here, and the concentration towards the plane is a perspective effect. And the central bulge This region here is 25,000 light years away. So you can see straight away the similarity between the image we've just looked at, the entire sky seen from the Earth, and this very distant galaxy. And you can see the similarities with the dust along the plane of the disk. And it's all confined to a disk, which if we were to look at from above, we will see appears to be rotating, and it is in fact rotating. So that's what our galaxy would look like if we could get far away from it. There we are, 25,000 light years, and here we have an image of a galaxy very like ours, and the sun, and of course all the other stars are orbiting around the center of our galaxy. Our sun is traveling at about 220 kilometers per second, feels the gravitational field of the galaxy, and it still takes about 220 million years to go around once. So we've been around the center of our galaxy about 20 times since the sun was born. Now, pictures of galaxies look pretty solid. And what we're seeing here is the haze of the 100,000 million stars or so, and the dust and gas, and places these red patches where stars are being born. So we can make a model of a galaxy, just to give you a feel for this. Now, fine Namib desert sand, like that you can see in my hand, which you can probably hardly see, but you see magnified on a millimeter scale down here, has a grain diameter of about 0.2 millimeters. Now, a cubic meter of that sand would fill 4 of those wheelie bins and will contain 100,000 million grains. So we could pour the sand out on the ground and spread it around, leave a little bulge in the center, make some nice artistic spiral arms, and we would have a nice little model of a galaxy. But then the challenge is we have to take a grain of sand, and we have to say, this grain of sand represents the diameter of the sun. How far apart must we move each grain of sand to get the right scale? Well, the answer is each grain of sand must be moved about 6 kilometers apart. So that gives us the right physical scale. And then, unfortunately, our model galaxy would stretch about 1/3 of the distance to the moon, which makes it unimaginably large. So we'll have to try a bit better with our model here. So if instead we imagine all 100,000 million stars are confined inside that grain of sand, then what will be, so that's, you know, they're all sun-sized stars, which of course is a bit of an approximation. So then how big will our galaxy be on that scaling? And the answer is the nearest star would be about 1.3 meters away, and our model galaxy would be about 30 kilometers in diameter. So I think I've probably convinced you that there's an awful lot of empty space in a galaxy. Now, when we look around the sky, we see that galaxies come in a large variety of shapes and sizes. And this is not a montage, it is just a bit of sky with a giant elliptical, an edge-on spiral, and that's undergone an interaction here. And it's got what we call a peanut bulge. And when you think of a galaxy and you see something like this strange peanut bulge, what we're looking at here is just a concentration of star orbits in 2 planes like that. Because each star in a galaxy has its own separate orbit in the gravitational field of essentially all the other stars in the dust and gas. And what we've come to realize is that galaxies grow and evolve not just by accumulating more gas that falls onto them and makes new stars, but by colliding and merging with each other. And that is what we see going on here. And I'd like you in particular to notice these long luminous tails. So let's see a simulation of galaxies colliding. And what we've got here are two disk galaxies that are at right angles to each other. And the simulation spans 1,000 million years. That's about a quarter the age of the Earth. Now, the only force at play here is gravity, and the white dots represent stars, and the red dots represent dark matter, which we're going to talk about, which in fact accounts for about 80% of the mass of this system. And again, notice how these streamers form during this collision. So this simple simulation that only uses gravity gives us a quite a realistic view of what happens when galaxies interact. So in this collision, again, we can see the streamers of newborn stars like those in the simulation. And the detailed image of this system, taken with the Hubble Space Telescope, shows bright luminous stars that have recently been born out of the gas clouds that have collapsed, these gas clouds, and the gas clouds can be seen as these dark grey or brown regions in here, but they have been stimulated into collapse by the tidal forces of this collision, this interaction of galaxies. Now, the stars, of course, will pass each other by, but the gas atoms or molecules, there are a lot of molecules, tend to collide with each other, which also helps trigger the collapse. The centers of these two galaxies, here and here, contain black holes millions of times the mass of the sun that will eventually merge. Now, we've talked about stars and we've hinted about this mysterious dark matter, and so we must talk about dark matter. And dark matter reveals its presence through its gravity. It's called dark because it does not interact with electromagnetic radiation, that's light, so it can't cool. When ordinary matter, like hydrogen and helium, is compressed by gravity, it heats up. That creates a pressure that temporarily halts the collapse. The heat is radiated away and the gas cools, allowing gravity to go on collapsing the gas cloud, which gets smaller and smaller until gravity takes over and the stars burst into light. Dark matter cannot cool because it doesn't interact with radiation that'll carry its heat internal energy away, if you like, so it remains inflated in diffuse halos around galaxies and clusters of galaxies. And there are 4 lines of evidence for the existence of dark matter, but unfortunately, we only have time to look at 2 of them. And those 2 are the X-ray gas in clusters of galaxies and gravitational lensing. And this, of course, brings us on to another aspect of the universe. And on the left there, we see a cluster of galaxies, and it's dominated by a giant elliptical galaxy in the center there, and all these other blobs are in fact galaxies surrounding the giant elliptical. And on the right, we see the same cluster imaged with an X-ray telescope, which shows a bright halo of gas that envelops the whole cluster and in fact has a temperature of about 80 million degrees. The bright source in the middle, a very bright object here, is in fact coming from a black hole, coming from matter in an accretion disk that is falling onto a black hole in the center of the giant elliptical galaxy. So it's called an active galaxy. Now, gas atoms, the temperature of 80 million degrees, move at a high speed. And to keep them gravitationally bound inside the cloud requires a much stronger gravitational force than is provided by the stars in the galaxies and even the halo of X-ray gas. So once again, we have to invoke this mysterious dark matter to do the job for us. And this estimate we see here made by Andy Fabian at the Institute of Astronomy shows that maybe 1 to 2% of the mass is in the stars that show up our lovely galaxies, the sort of thing we're used to looking at. 11% of the mass, that's 10 times as much mass, is in this X-ray halo, and that leaves 87% for the mysterious dark matter that is required to confine the gas in the halo. Now, you might say, gosh, if we're bathed in gas at that temperature, surely it destroys everything. But of course, the densities are very, very low. So even if our solar system was bathed in such a gas, it wouldn't really be having much effect on the Earth, only a few atoms per cubic meter or so. And anyway, we have the heliosphere of the sun that protects us from ionizing. These particles would be highly ionized. So not something we would have to worry about. So that takes us to really what some of the most spectacular evidence for dark matter is called gravitational lensing. Now, this is something predicted in Einstein's general theory of relativity and first observed in the tiny deflection of starlight, star images, I should say, starlight, during an eclipse 101 years ago, which was we celebrated last year, which was a great confirmation of Einstein's theory. Now, notice the concentric arcs, which are the images of distant galaxies. In fact, you can see some little dots in the arc here, and you'll see similar dots in the arc here. So many of these arcs are, in fact, images of the same distant galaxy. So what is going on here? So this is how it works. Rays of light from the distant galaxy travel out in all directions, and some that would be passing past us by are, in fact, as they come near this intervening massive cluster of galaxies, the light is lensed or refracted, bent by the gravitational field. And so when it arrives at the human eye, comes in at this direction in our telescope, and we think it comes from up there. So we'll see an image of the galaxy up there and another one similarly down there. So that's how the process works. And here is an extraordinary, a very rich field of galaxies with many arcs. And once again, it's the same old story. The amount of normal matter is not sufficient to cause such strong lensing. Now, lensing has another great advantage for astronomers, because it not only increases the size, but also the brightness of the distant galaxies. And so it enables us to observe background galaxies that would otherwise be far too faint for us to observe with our telescopes. And we think, and some of the images in this field come from light that was emitted when the universe was only about between 500 and 1,000 million years old. Now that is round about the time when the first stars burst into light, but these are not the first stars, because we already see the gas is enriched with heavy elements. So we don't know what the nature of dark matter is, but we do know some of the things that it is not. It is not literally dark matter, like interstellar planets that would not be luminous, or dead stars, or cold dust and gas. And of course, there are much speculation about the nature of dark matter. There is even a not widely favored school of thought that maybe dark matter can be explained by a need for a modification, if you like, of Newton's laws or general relativity at very low masses. But not many people believe that. So dark matter is a big mystery. So now let us move on. We have to do a lot of rapid moving on in this talk. And let's get to, in 1929, when Edwin Hubble published a paper showing how the Doppler redshift of the spectrum of nearby galaxies, or to put it another way, the velocity with which they're traveling away from us, increases with increasing distance. And this led to something called the Hubble-Lemaitre law, which simply describes how an expanding universe works. I mean, how galaxies move away from us with a velocity proportional to the distance. So a galaxy twice as far away from us will seem to be going twice as fast. And he was able to essentially calibrate this law by observing variable stars in distant galaxies and comparing their brightness in our own galaxy, which is something that we are doing up to the present day. Now, this cluster of galaxies, and the fuzzy things are the cluster of galaxies, the stars are all in our own foreground, in our own galaxy. We always have to look through our galaxy to see what's going on elsewhere. This cluster is at a distance of about 60 million light years, close enough for the Hubble Space Telescope to measure the brightness of individual variable stars in these galaxies. But and what we can do is compare their brightness with similar stars in our own galaxy and use the inverse square law, and that enables us to work out the distance of the galaxies in kilometers. At the same time, we can measure the redshift, and this shows that they're moving away from us at quite a substantial speed of 1,500 kilometers a second. And this is significantly greater than the random velocity of the individual galaxies, because they're all moving around their own center of gravity. So with a known distance and a known velocity, we can work out the expansion rate of the universe, and this is referred to as the Hubble constant, 73 kilometers per second per megaparsec. A megaparsec is 3.2 million light years. So that's the way we express it. We do the thing that we're all taught never to do at school. We mix kilometers and light years, if you like. In this, it should really be kilometers per second per kilometer, but then it turns out to be a very small number indeed. So if we look at this picture here, I'll ask you to ignore the wonderful galaxy, interacting galaxy spanning the whole image, but you will see the sky is filled with very faint galaxies, many galaxies all over the place, just a few stars in our own foreground galaxy. And all we have to do to find their distance is measure their redshift and use the Hubble constant to convert this into a distance. So this is something astronomers did some years ago. They took two strips of sky opposite each other in the sky, about 70 degrees opening angle, and measured the redshift of 250,000 or so galaxies, all the galaxies they could see, and then they plotted this map. It's complete, the plots are complete out to about 1,000 million light years, and you'll see there's a thinning here. This is not telling you what the universe is like, it's just that you could only see the brightest galaxies at this distance, so it's complete out to about 1,000 million light years or so. And note the filamentary structure and how this kind of foam-like structure, if you like, these holes and cavities and filaments, and how it's qualitatively the same all over the sky. It's the same over here as it is in the opposite direction here. And this is a very important part of the structure of the universe. It tells us on the largest scale, the structure of the universe is pretty uniform. And just to sort of jump forward in the story, if you like, this foam-like structure arises from the microwave density fluctuations that we see. So this is a scale of 300 million light years or so, and goes back to tiny quantum fluctuations in the very early universe. Now, we calibrated the Hubble law out to a distance of about 100 million light years. That's as far as we can go with the Hubble Space Telescope to see these Cepheid variables. And so what we've done is to assume that law applies and extrapolate it to plot the map that we've just looked at. And extrapolation is very dangerous in science. So we need another method to find the distance and check the Hubble law and whether it's accurate. And so this is provided by a very special type of exploding star called a type 1 supernova. And there it is in the bottom there. And these stars, when they explode, for a few weeks, they can outshine an entire galaxy of 100,000 million stars. And they always go off with about, give or take a little bit of correction here and there, with about the same luminosity, so they are a very handy standard candle. So we have two ways of measuring distance. We can look for supernovae in galaxies, and these are quite rare, so it's only when we look very deep into space that we see so many galaxies and clusters of galaxies that every month there'll be a few supernovae. And here is an example of a cluster of galaxies at a distance of not 60 million light years, the age of the dinosaurs, if you like, but 8,000 million light years. So the light from this cluster and this supernova, see the hot pixel there it is enlarged, has been traveling across the universe towards our telescopes for almost twice the age of the Earth and Sun. The supernova is fainter. What we find is it's fainter than we expected from the observed redshift, indicating that the cluster is in fact further away than the redshift predicts using the Hubble constant measured for nearby stars. In other words, the Hubble constant was smaller in the past. This implies the value of the Hubble constant is not constant, but increases with time, which means the expansion of the universe is accelerating. And the only way this can be explained is by invoking the existence of some mysterious force or pressure causing the universe to expand ever faster, which is called dark energy or vacuum energy, not to be confused with dark matter, as I nearly did then, dark energy or vacuum energy. And these results were first published by two independent teams back in 1998 and led to the award of the Nobel Prize in 2011 to the team leaders, Perlmutter, Schmidt, and Rees. Not Martin Rees, Adam Rees. The data above shown here are from a more recent survey, and it's not obvious that the slope of brightness against redshift isn't in fact a straight line. It does turn up at the end there, and the differences are shown in the bottom diagram. When we look over this side, we're looking at distant galaxies, showing the universe was decelerating in the past, followed by acceleration today, and the nearby galaxies are over here. So this is close to us, and these are far away from us. So let us just pause for a moment to see what we have done. And what we've got here is a diagram with time along the bottom and distance. I put distance between two objects. It's the scale of the universe, if you like. And today is a line down the middle here. So the past is here, which we can observe, and the future is there, which we can try and predict. And what we've got here, the slope here, corresponds to the value of the Hubble constant. And so what we're saying is that we can go back, the universe is expanding at a certain rate today, so we can predict when it had zero size. Then we say, well, that's the age of the universe. It's called the Hubble time, technically. So that is a simple understanding of what we did and how essentially we predicted what happened in the universe. And we know that this is not actually what we observed, but let's just follow this through. So we've just found that the universe does not expand at a constant rate. We've found that. And this should not come as a surprise, because both Newton and Einstein tell us that the force of gravity of matter in the universe will slow down its expansion. And here are three possible pasts and futures. You will see, but they, of course, when we model them, they must all have the same expansion rate today. And notice that they go to zero at different points along the timeline, so they give different ages. They would give different ages for the age of the universe. A low-density universe will expand forever. A critical density universe comes to a halt at infinite size, and a high-density universe with lots of mass stops expanding and starts contracting, coming to a big crunch. This is a bit like if you toss keys in the air, the gravity of the Earth, they go up, and then they come down again. If you fire a bullet at a speed of 11 kilometers per second or so, it will just go on and on, expanding forever and ever. So these are the possibilities for the past and future of our universe. And what we observe, and what won the Nobel Prize, is that none of these three conditions apply. And here we see initially the universe decelerated in the past. You see it's curving over like that. And then about 6,000 million years ago, it started to accelerate. And of course, it has to have the same value of the Hubble constant today, but we would predict that that acceleration will continue into the future, driven by this mysterious force. Now, I have to say, these diagrams greatly exaggerate the effects that we are looking at. Now, Einstein's theory of general relativity is the appropriate theory for describing the universe, although, as ever, we can use Newton's approximations to get a good understanding of things. And Einstein has two important things to say. Mass and energy are equivalent, and pressure, mass, and energy are all equivalent, and they not only exert gravity, but they feel gravity. So mass energy, we can stick that together and talk of mass energy, and like we can of space-time. And Einstein says the density of mass energy, well, it defines the shape of space-time, it defines the geometry. So we don't have to try and work out what's the density of mass today, or energy and everything else. We can try and find the geometry, because low densities give a hyperbolic geometry. The critical density, which comes to a halt at infinity, gives us a Euclidean geometry, and the density of something that recollapses is spherical, just like the ultimate twisting recollapse of space-time is around a black hole, where the space becomes completely wrapped around the black hole. So our challenge is to find the geometry of the universe.
Robin, just to say there that
yes,
we have so many questions that you've sparked.
Oh dear, yes. Okay, well, I'll try and wrap this bit up fast and get to the end. Is that what you're telling me? Yes.
As long as it's not the end of the universe.
No, well, not quite. No, we can discuss that. Yes. So we can go to our microwave background to find the geometry. And in fact, what we have to do is look at this little mottling at the angular scale of these tiny little mottles, which correspond to the distance that light has traveled in the first 370,000 years when this image was formed. And we know the physics of that. So if we can measure the angular size, we can work out what the geometry is. And we find it is the critical density type geometry. It is flat and Euclidean. And that allows us to put together the story that we have found and come to a very simple conclusion. The geometry gives us the total density of matter and energy. The expansion rate fixes the ratio of matter to energy, and tells us what the fate of the universe will be, and various observations fix the ratio of dark matter to normal matter, which allows us to plot this extraordinary composition of the universe, that the stuff that we and stars are made of only makes 5%. Dark matter, the mysterious dark matter, makes about 27%. And the energy of this expanding, accelerating universe works out to 70%. Now, I have to say, this is the way it is today. When the universe was very young, dark energy contributed nothing. In the far distant future, dark energy will overwhelmingly dominate all the other energies, although the universe will have the critical density. Okay, we won't stop with that. We'll just finish our story of journeying to the edge of the observable universe by looking at an image taken with the Hubble Deep Field. The Hubble telescope images about 100th the area of the moon. And what they did was expose on an area of sky for 2 million seconds. That's about 22 days. In fact, they added together thousands of individual images to get this image, the deepest image of the sky ever taken, the Hubble Deep Field. We look back to a time when the universe was about 1/20th of its age, and we see the entire history of the evolution of galaxies. If we could rush over to see the faintest points in this image, they would not be there today. They would have merged to form big galaxies like the ones we see closer in the foreground. Now, the simplest thing we could do with this image is count the number of galaxies, scale it up to the scale of the whole sky, and then we would come to the amazing conclusion that there are 100,000 million galaxies in the observable universe. We've already spoken of the 100,000 million stars in a galaxy, so this is my favorite number, you see. And, well, there are probably only 86,000 million neurons in the human brain, but to bring us back into the picture of complexity, but our brain with its multiple connections, the number of possible connections of those 86,000 million neurons far exceeds any number we'll see in astronomy. And I think I will stop now and just leave this image showing the places we visited, how we, looking back in time, we calibrated the expansion here, plotted this diagram out to 2 billion light years, birth of the sun, our lovely gravitational lensing, our supernova survey that showed the universe was expanding, and the Hubble Deep Field and the microwave background. And one of the great triumphs of modern astronomy is the fact that we can have a simple 6-parameter model that will start with this as the starting point and evolve a universe that ends up with this structure. Okay, I will stop now. Thank you very much. And shall I?
Robin, thank you very much indeed for that wonderful talk. Welcome to the 4,467, well, that's screens. There are probably many more than that, actually, maybe up to 10,000 people listening to you tonight, Robin. What a marvellous talk.
Thank you, that's amazing.
Straight in with Tarek's question, why can we look backwards but not forwards in time? Will we be able in future to be able to look forwards?
That is a very profound question, actually, why we cannot look forward in time, because it depends on your view of the universe, of how deterministic it is. But essentially, the future has not yet been defined, would be the simplest way of putting things. So we can have no knowledge of it. There's no evidence that people in the future are traveling back in time, which might indeed be a possibility. Although if they did travel back, they wouldn't be able to influence the past. In other words, they wouldn't be able to come back and murder their grandparents.
And can you prove that there's nobody from the future who's looking, is one of those 4,467?
No, we can't prove that. What can we say? Yeah, I think we can't prove that, but I think if if they were having some influence, then they might come back and be changing things on our behalf or something. I don't know.
Panima says, could the universe already have finished on the outer limits, but we won't know about it yet?
That is a possibility, that people talk about a great rip. Anything like that, a change of state, a change of the 0 point in the vacuum energy or something that may be associated with this inflation, would travel at the speed of light. So we would not know about it. We would be, one moment I'd be talking to you and the next moment I wouldn't, and I would not have the consciousness to realize that I was no longer talking to you. So if it happens,
talking, Robin, we feel much safer. Lucy asked, who's a Buckingham university student, asked a question early, but I think you've answered that, which is the difference between dark energy and dark matter.
Yes.
Stuart A says, what came before the Big Bang?
Now that is a very good question as well. And 20 years ago, I would have said you can't, that is an unanswerable question, because nothing came before the Big Bang, because time and space originated at that moment. But we now have people called string theorists and a brain theory that suggests that the universe may have far more dimensions than the 3 of space and 1 of time. It may have more dimensions of space that are on a much smaller scale than the 3 of space. And essentially, the universe may have arisen from a collision of 2 brane surfaces in this higher dimensional structure. Or it's possible that inflation, there's no reason why inflation, the accelerated expansion of the universe, should go on forever. It may slow down, reverse, and we may go through a big crunch, in which case our universe may not have started with a singularity. It may have started with a multiplicity of singularities that came slightly before and after each other as a previous universe collapsed to form our own. And it may be possible to distinguish those 2 theories in the future by looking at gravitational waves or something.
We're going to carry on till just after 5 past, because there's so many great questions. We normally stop sharp at 7. Adam Davis says, what's inside a black hole? And if we don't know, do you think we would get to the point where we could find out?
Right. Well, hopefully we might get to the point where we could find out. And if we do, it will be through the string theory. It will be through the unification of quantum physics and general relativity, which general relativity describes gravity and space-time. And as you know, gravity is a very, very weak force. The string theorists would say that it's a force that extends out of our 3 dimensions of space into higher dimensions. That's why it's so weak. So that is the only physics that will explain the singularity of a black hole. Otherwise, we do not know the answer. It's nice to know that there's an awful lot out in the universe that we do not understand. When I give this kind of talk, it almost sounds as though I've got a lovely complete picture, but there are all kinds of problems out there still.
Amber says, why does conventional physics predict a cosmological constant that is vastly too large?
Now Amber may well have heard that there is, oh, I know, sorry, yes, that was, I thought she was talking about the Hubble constant. Well, it's a consequence. You'd have to ask a quantum physicist that. Basically, what she's saying is that what we find is that this acceleration of the universe is relatively slow. That if we look at quantum physics and look at add together all the fields that exist, the particle fields, then we would expect the cosmological constant to be, is it 10 to the power of some enormous number bigger than it is? And so this is just another example of the lack of understanding, is the mismatch between general relativity and quantum physics.
Yeah. Patrick asks, how can Einstein gravity be reconciled with quantum mechanics? And another question there is, will another Einstein come along, perhaps already born, who will vastly enhance our understanding of the universe?
That is the answer to that is probably yes. We seem to be at a little bit of a stalemate. String theory, which is the theory that will perhaps bring this unification of quantum mechanics and gravity, is our best hope. It's been around for quite a while, and it has not yet managed to make a successful prediction that can be tested in the observable universe. Some people have said that the idea has come many years too early, that we don't have either the mathematics or the insight to fully understand what quantum physics, even quantum physics on its own, quite apart from unifying them, is trying to tell us. So yes, I'm sure physics is not at the end. And the sobering thing for me was realizing that Newton, after his work on gravity and his work on optics, spent time trying to unify gravity and light. And we would look back and say, wow, that was far too far before its time. And maybe we are in a similar quandary.
Jane asks, Robin, what new astrophysical objects are still awaiting discovery?
Well, of course, if I knew the answer to that, I would go and discover them. But can I make a more sensible answer there? Well, no, I don't think I can. I think where we are trying to understand is we are pushing back, understanding the physics of the universe way before it was a millionth of a second old, and the universe went through a period of inflation, very rapid, when it was about 10 to the minus 36 seconds old, which is why the microwave background seemed so uniform when light had managed to travel literally only a degree across that space. And that, I think, when we have better gravitational wave detectors and so on, we may be able to unravel, and we may discover something new there.
And Richard's asking there, what is the origin of inflation, and is there direct evidence of it? So we've looked a bit at that. Let's come on to Amy, who's asking about the origin of entropy, and is there direct evidence? So she's asking about entropy.
Yes. Entropy is a tricky one in the universe, and it does seem to be a very fundamental principle in physics, and I'm not sure what the best way to approach it is, whether it is a matter of probabilities, that entropy is just saying that as things change, there are states that are far more probable than others. So but it is very fundamental. It must be tied up with the arrow of time, which again is a mystery, because as you know, in particle physics, a reaction that can go one way, a proton and a neutron, or a proton and an electron, can just as well go the other way. So entropy is definitely something to do with time. And I talk to my string theorist friends, and they will say, oh, well, space and time, they're both what we call emergent properties, in the same way that temperature is a consequence of the atomic behavior of atoms whizzing around at high speed. And they will say, well, it's possible that time is an emergent property. It's some artifice that we see, but all a big mystery, and I'm a poor, simple observational astronomer.
Don't put yourself down. Will says, why do some astronomers believe in God?
Oh, I think as a general observation, I think there's no correlation with a belief in God and a particular activity. There are scientists and astronomers who do not believe in God, and there are very distinguished scientists and astronomers, if I think of George Ellis, a cosmologist, who do believe in God. Now, there is always an ultimate mystery. When you say what came before the Big Bang, then I maybe tried to give an answer there, but all I did was to push back that fundamental question of where does it all come from, just a few more stages. So there is an ultimate mystery. And I think until we can confidently explain what consciousness and self-awareness is, I don't think we can expect to tackle the question of whether or not there is a God. And I think we're a long way from that. And in fact, I think there may even be a kind of principle like Gödel's incompleteness theory of mathematics, that we will never completely understand a universe of which we are a part. So belief in God is a matter of belief, and it doesn't correlate with scientific knowledge. Nothing I've said today either proves or disproves the existence of God.
Two final questions, and I'm so sorry I can't take more. William says, is our universe stable?
Well, yes and no. It went through this incredible period of inflation where it expanded many e-folding times, we think, very early on. It is now slowly starting to inflate again. It's stable on the lifetime of the Earth and the Sun. Earth's got 7,000 million years to go before it pops into the Sun. It's stable on that time scale. Whether it's stable on thousands of millions of years, we don't know. Possibly not.
I'm just going to give you a range. Anton is asking, is information lost in a black hole? Kim says, are there higher dimensions? Rachel says, what are the origins of space-time? Jason, what will be the main focus on space going back to the moon or going to Mars? Well, perhaps what should it be also? Adele says, what explains relativity and Einstein's gravity? Adam, another Buckingham student, says, is physics mathematically consistent? And Frankie says, could you explain the difference between dark matter and dark energy? So take one of those and
oh my gosh, that is,
and you have about 30 seconds.
A challenge. And in fact, most of those questions are unanswerable. And so they are a challenge.
That's no excuse.
Yeah, I know. Well, that is the challenge to the next generation and what makes this field so exciting. Maybe the easiest one to take is dark matter and dark energy. It is just possible that they may somehow be related, but dark energy is something that is causing, it seems to be associated with empty space. It is something related to space. It's like an extra force field in quantum physics. It would be another field. Dark matter will probably turn out to be something physical, like a particle of some sort. So it's something, and what it is, it's extra gravity. It manifests itself through gravity. So there's no doubt that gravity and space and time are all related, so they may be in that mix.
And yeah. Two quick final questions from me. What in your lifetime, Robin, has been the greatest discovery in astronomy?
Well, I think, in my lifetime, what I've seen is the unification of astronomy. And so we had many disparate fields, and now they've come together to be able to tell the story that I told this evening. And I suppose if I had to pick one thing, it would have to be, well, in my lifetime, because that excludes general relativity, it would be the accelerating expansion of the universe. I guess that would be it.
Second, and this is a yes or no, I think I know what the answer is going to be. Do you think that astronomy should be taught to every child in school?
Oh, yes, I do. Yes.
And so do I. And when I was ahead, that's absolutely what I wanted to do. And the third question, which everybody is dying to know the answer for, and this could be either from the universe or indeed from film, assuming that film isn't in the universe. Name your greatest star, your favourite star.
Well, I'm afraid I'm going to bore everybody. It's a star called UY Centauri. So it's a variable in the constellation of Centaurus in the southern hemisphere, and it had a very peculiar spectrum. It's full of rare earths, all the things we need to make batteries today. And it was the subject of my thesis. So I spent a lot of time.
Very understandable that you have that love affair, which is which will be confidential to all of us. And finally, to show your multidimensionality, who is your favourite film star? Without thinking.
You know, I don't really have a favourite film. Anouk Ami, I'm going to who I had pinned up on my office, came from a film called A Man and a Woman back in my student days, Anouk Ami, and I thought she was wonderful.
Well, there you are. That was totally unpredictable and totally delightful, as was this whole talk, and making the case about the importance of the life and of the mind, and everybody, humanities, social sciences, scientists, all need to understand more about astronomy, the universe, and you have given us the most brilliant talk about it tonight. Have a good weekend, everybody. Thank you very much indeed, Robin Catchpole, for a wonderful talk.
Thank you very much. Thank you, everybody, for coming. Thank you.